Hey folks, this video is about extending the ideas of optimization from what we learned in our Calc 1 class to functions of two variables. So, well, let's start by reminding ourselves how we did this back in Calc 1. So this was one of our first applications of the derivative. The idea was if we wanted to find extreme values for a function, we would start by finding the critical points, that is, the places where the derivative was zero or didn't exist. And then we had some tests to see if these were maxes or mins. So let's look at this question. We want to optimize this function f of x on the domain from -1 to 3. We can start by taking the derivative of f. We want to know when that's equal to 0, so we can solve. I'll factor here to make that easier. And we find that there are two critical points, -1/4 and when x is 2. So there's the first derivative test. I'm not going to use that here because that doesn't generalize. And the second derivative test. The second derivative test has us check the concavity at each of these critical points. So we can do that. We can see when x is -1/4, our function is concave up. And if you think about it for a moment, well, what does it have to be if a function is concave up at a critical point? Well, it has to be a local min. And at the second point, we see there's no concavity. And unfortunately, that doesn't give us any information. So we have to appeal to some other way. And if we have a graph, well, that's a perfectly good way to see what's happening. And we do have a graph here. So you can check that when x is -1/4, we've got a local minimum. When x is 2, we've got a saddle point. That is, it's not a min or a max. But we haven't answered the question yet. So at the endpoints of this interval, we have two local max points. But if we're looking for a global min and a global max, well, then we'll check all of our extreme values, both the endpoints and the critical points, and find that, yeah, we've got a global min at x equals -1/4, global max at x equals 3. All right, that's old business. New business. If we've got a function of two variables, a local min or a local max occurs at a point where, well, maybe let's pause. What do I mean when I say local max? We mean the same thing as we did in Calc 1. It's a point that is higher than all of the points around it. And I'll use the term the neighborhood, which actually is a term we use in higher math. And a local min would be defined analogously. It's lower than all the points right around it. So if we've got a max or a min, then the gradient has to be the 0 vector, that is 0, 0. And I'll give you two ways we can see why that's the case. Remember, the gradient is made up of partial derivatives, the partial with respect to x, partial with respect to y. If either of those partials was a non-zero number, we could increase by going in one of those directions. If the partial with respect to x was positive, we could get something higher by going in the x direction. Or if it was negative, we could get something higher by going in the negative x direction. And the same could be said about y. So at a max or min, both of those partials have to be 0. Another way to see this is, remember, the length of the gradient vector is the greatest slope we could find from traveling away from a point. Well, if we're at the top of a peak, there is no greatest slope. We're there. Right? So the gradient vector has to have a length of 0, and, well, the 0 vector is the only one that fits the bill. And these are the points that we call critical points. when we're talking about a function of two variables. So let's try it out. We've got an example here. I want to find all of the critical points, that is the places where the gradient vector is equal to 0. So I'll take a second to write down the gradient vector. That's the partial with respect to x and the partial with respect to y. And if we want this to be 0, we need both components to equal 0. So we're solving a system of equations. It's easier to solve the second equation first. Well, not to solve it, but to find that y has to equal x. And then we can plug that into the first equation to get this quadratic. You could use the quadratic formula, or we can factor, and we find that the solutions are when x is minus a third or x is 1. But remember, y was equal to x, so we get 2 critical points. At this moment, we don't know yet if they are maxes or mins or saddle points. Well, why don't we take a look in Sage and see what we can tell from the contour plot and from the graph. So in this Sage worksheet, I've input this function f of xy that we just looked at, and I've asked for the contour plot. Remember, our critical points were at minus 1/3, minus 1/3, which is around here, and 1, 1, which is around here. So looking at the point 1, 1, you might observe that this is probably a local minimum. We see the z values are decreasing. But we'll zoom in on both these points, and it's kind of hard to tell what's happening here. So zooming in, getting a tighter view of the point at 1, 1, we see, yeah, for sure, this is a local minimum. The z values are decreasing, and right in there, we would have the bottom of a crater, sort of an elliptically shaped crater. And at the point minus a third, minus a third, minus a third, we see, well, sort of to the northwest and southeast, things seem to be increasing in both those directions. So if we were to cut a diagonal cross section here, it would be concave up, whereas to the northeast and southwest, it's decreasing in both directions. So if we cut a diagonal cross section here, it would be concave down. So this is a Pringle shape or a saddle shape. So it's neither a max nor a min, because there are points around it that are bigger and points around it that are smaller. So we can take a look at the 3D graph to see both of these things represented. Here I've put a yellow dot at the saddle point, so we can see in one direction it seems to be the highest place in town, but in another direction it's definitely not, and it's the lowest. So there's our saddle shape, whereas here's the point minus the point 1, 1, which is indeed the lowest in the neighborhood. It's not a global minimum. We can see there are z values that are lower, but locally it's the smallest. So we've got a local minimum there.